Hello, my name is Vicky Yan. I am trained as an applied mathematician and I'm now a fellow at the Santa Fe Institute. Today I'll be talking about predicting the limits to social learning for good collective decisions. I'll present a mathematical model that accounts for collective decisions when we have a mixed decision-making type. One is social learners, one is individual learners. So social influence has been an important aspect of collective decisions. However, there are many conflicting findings in this area. So some research finds that it hurts collective decision accuracy and qualities. However, some find that they improve the collective decision accuracies and qualities. And in some research finds that both can occur. The problem of social influence is most visible when we're considering systems of uninformed individuals where their decision making is dominated by social learning. In political science, uh, research have found there is a significant part of the voting population who do not know basic facts about the government or policy, and that will hinder good democratic decisions. However, in animal research, some find the opposite. For example, small groups of informed individuals is found to be enough to lead a large group of uninformed ones. Also, uninformed individuals can also promote democratic decisions. So the goal here is that I want to reconcile these conflicting findings through a simple mathematical framework. I want to also be able to say something about a boundary of how much social learning a system can contain while still making good decisions. So here I will present to you a mathematical model where I consider a mixture of individuals using individual and social learning heuristics. The setup of the model is the following. I consider binary position X and Y on an issue in a well-mixed situation. So I also consider two types of decision makers, individual learners, those who think for themselves and make decisions based on information, and social learners, those who make decisions driven by how many other people take on each side of the issue. I also assume that decision-making type is uncorrelated with the kind of position taken. Here are some more details about the model. I consider portion R of the population to be individual learners and portion 1 of R to be social learners. People also do not switch between decision-making types. Among individual learners, I denote Xi to be the portion that hold opinion X, and Y minus Xi is those holding opinion Y. And people can transition between these two opinion states. So Pxy is the rate of people transitioning from X to Y, and Pyx vice versa. The similar picture happens for social learners. The only difference is that the sub and superscripts are changed from I for individual to S for social. Now we can write down a set of conservation equations. These two equations are very similar. One is for individual learners and the second is for social learners. So this equation says the rate of change for people holding opinion X is composed of two parts. One part is the flux in, is those who hold opinion Y transition into opinion X. And the second term is to minus the flux out. That is, people holding opinion X transition into opinion Y. And the same happens for the social learners. The next step of this model is to become more specific about these transition rates. For individual learners, I introduce this parameter called the relative merit of a position X. I denote it as M. M is a number between 0 and 1. M equals to 1 suggests that when a new piece of information comes in, everybody would prefer X over Y. And M equals to 0.5 denotes these two positions are equally of equal merit. So this kind of framework can also help take into account a population with heterogeneous preferences. So not everybody prefer the same thing. So for individual learners, they are only affected by this information they gather, and their transition rates from y to x would be m, and by symmetry from x to y would be y minus m. So the equation for individual learners can be written as below, where the transition rates are replaced by these two terms. Now we consider social learners. The transition rates from y to x, I call it a function f of x. That is the frequency-dependent conformity response function. Here, x is the portion in the whole population, not just the social learners, that hold opinion x. So from the psychology literature, this response function should be an increasing function and is always often written as a symmetrical around the midpoint. So here's an example of such a function. It's written in this piecewise form with one free parameter alpha. And the value of the alpha will determine the curvature of this function. And some examples are shown in this picture. So in blue is a case when alpha is greater than 1. You have this sharper transition around this 50-50 split. When alpha is smaller than 1, you get the orange curve, which is of opposite convexity. And with alpha equal to 1, you get this linear response. So in the empirical literature, we find that alpha greater or equal to 1 are often observed in human and animal systems, where in the psychology literature, they would call this blue curve a conformity response and this dashed curve the anti-conformity response. So the equation for social learners can be written as the following, where f is this function replacing the transition rates. In the result that I will show later, most of them will be using this particular example of conformity function. However, we also have some analytical results without a specific functional form, but only considering this general properties of f, and we still find some similar results. Okay, so when we analyze this dynamical system, we focused on analyzing the fixed points and their stability. So in particular, the fixed point about x, which is how many people in the whole population hold opinion x. Here I'm showing an example of the portion of individual learner R is 0.4. In this case, the high merit option is always preferred by the majority as well. What becomes more surprising is that when the portion of individual learners decrease below a threshold, we start to see a bifurcation occur. That there is this unstable region in the middle, and in this mid-range M, we either stabilize at the upper branch or the lower branch. So both options can be preferred by the majority, and we wouldn't see a system sitting on this dashed line because even though the derivative of x is 0 at that point, but this fixed point is unstable, meaning with small perturbations, it would either go to the upper branch or the lower branch. Please also note that this kind of system exhibits hysteresis. So the behavior of the system is history dependent. For example, if I have a issue where x has high merit, if I started over here and the merit slowly decreased over time, what we'll see is the system will first follow this upper branch until this critical transition point. And as M further decreases, it will jump down to the lower branch. However, when M increases again, it will not reverse this jump, but instead it will follow this lower branch until M crosses the second critical point, and then it will jump back up again. So one critical thing to understand here is where does this critical transition in R occur? And here's a picture to help us see that more directly. On the left panel, I'm showing a case where the two issues have equal merits. So when there are more individual learners, we see the system stabilize at a 50-50 split. However, when there are more social learners, we see the system either stabilize at either the upper or lower branch, despite the two options, not one is better than the other. So there's some sort of herding that happens in this regime. On the right-hand side, I'm showing a case where m is 0.6. So what we see is the symmetry of this pitchfork bifurcation is broken on the right-hand side, and we see this unstable state has some curvature here. So what we can solve for is where does this critical transition happen, or the critical R under which we see a bistable state. So here I'm showing the critical R as a function of alpha and for 3 different values of m. So if a system falls underneath the curve, we'll see a bistable region. We also showed some analytical results for general increasing f of x, that's without assuming this functional form in the special case of equal merit. We can show that the critical R is actually analytically solvable. It takes a very simple form that has to do with the derivative of the conformity function around the point 0.5. So in order for RC to have a solution between 0 and 1, we actually require this derivative to be bigger than 1. That is, the population needs to be more sensitive around this 0.5 region in the conformity response. And this also suggests when alpha equals to 1 in the linear conformity case, we get RC equals to 0, so this point. And for alpha smaller than 1, there will be no bistable states in the system. In the model I showed before, we made this pretty big assumption of the dichotomy between social and individual learners. However, in the real world, people tend to fall on the spectrum. So here we want to show an extension of our model into the spectrum version and show that our results are still preserved. For each individual k, the probability of transition between x and y is as the following. So the first term is the individual learning term, which has to do with the merit. And then the second term is the social learning term, which has to do with the conformity response. And here our k is a slider bar that goes between individual and social learning. So greater R means more individual learning. Here are some numerical results by simulating a few hundred individuals in a well-mixed system. So on top, I'm looking at the histogram of R for this population. On the bottom, showing the corresponding diagram of exit convergence as a function of M. So when R is more uniform, we see this smooth but nonlinear dependency in M. However, when R is more skewed to the left, meaning more people tend to be social learners, we see this bistable state occur, which is similar to what we see before. Here, we won't be able to see this middle unstable branch because of the simulation results, and the system won't stabilize there. So our model characterized collective decision system into 3 parameters, 2 for the group and 1 for the issue. And the next thing we want to do in the future is we want to measure these parameters in real world systems, both observational and experimental. We've been finding that quite difficult, in fact. So welcome any suggestions from the audience. I also would like a more sophisticated consideration of information or good. That is, what happens if there are correlation information or there's no constant flux of information coming in. So to conclude, I have proposed a dynamical system model for collective decision making with social and individual learners, and we predict a limit of how much in social learning a collective decision making system can allow without affecting the majority preference. And we would like to characterize these parameters which distinguish a broad range of group level behavior. So in the end, thank you very much.